In today's lesson, we'll be talking about 11.7 and 11.8. And to start, we'll begin with 11.7, ratios of area. What you've probably learned in the past is that when you do ratios of area, you would calculate the area of one figure and then compare it and reduce it to the area of the other figure. So if I have the two figures and I'm taking the ratios of the areas, I would calculate them each separately. So the area of the triangle would be half times 6 times 8. And to find the area of the parallelogram, I do base times height. You get 24 for the area of the triangle and 96 for the parallelogram. And then you would just put those in a ratio and reduce. And then the ratios become 1 to 4. Let's take a look at these triangles. Let's say that we were given the fact that the angles were congruent for there and here, making them similar triangles. And let's say that this was 3, and this was 6. And let's compare the areas of those in a ratio. For the smaller triangle, we'd again do half times base times height. And then the ratio would be over the larger triangle, which would be half times its base times its height. What you should hopefully notice right away is that the halves would cancel out in the ratios. And if I say that 3 and 6 are the bases, then I'll have h1 over h2. The ratio of 3 to 6 is 1 to 2. Therefore, no matter what this side is, this has to be double it. So I can go ahead and put that in. And that reduces to give you 1 over 4. Now if you go back and think about comparing 3 to 6, if I have 3 over 6, that reduces to 1/2, and 1/4 is just the 1/2 squared. And that takes us to our first theorem. If two figures are similar, then the ratio of their areas equal the square of the ratio of corresponding segments. Basically meaning if you know that the two figures are similar, you don't need to calculate each area, you just need to find the ratio of one side to another and square it. If we look at this example, we are given that AM is a median of triangle ABC. And we want to find the ratio of triangle ABM to ACM. So if AM is a median, that means that this is congruent to this. And this actually does not fit our last theorem of similar figures. Okay, we don't have enough information to prove that the triangles are similar. So we don't have much information, but we do know that this would be congruent to that, so we can label those X. And X happens to be the base in both triangles. So then what we have to then think about is what else would be needed to find the areas of these figures. We would need the height. So we would draw the height becoming a perpendicular line, and we can label that y. Now, let's compare the two areas. The area of triangle ABM over triangle ACM. And again, we're going to use half times the base times the height over the same formula. The halves will cancel out. In triangle ABM, the base is x and the height is y. And if we look at triangle ACM, right here, ACM, the base is also x and the height is also the same, which is y. From there, what you should realize is that the x's and the y's cancel out and you're left with a ratio of 1, meaning that the area of triangle ABM is congruent to the triangle ACM. And that brings us to our second theorem. A median of a triangle divides the triangle into two triangles with equal area. And the second part of today's video is 11.8, Hero's and Brahmagupta's formula. They're just simply two formulas that can help us calculate the areas of a triangle and a quadrilateral. The first one, Theorem 111, is called Hero's formula. And you can take the three sides of the triangle, and you do not necessarily need to know the height, and you can calculate the area by doing the square root of s times the quantity s minus a times the quantity s minus b times the quantity s minus c, where a, b, and c are the lengths and the sides of the triangle. S stands for the semi-perimeter, meaning you take the perimeter and divide it by 2. Theorem 112 is Brahmagupta's formula, and it follows a similar pattern. You're going to take the square root and you will multiply it by the semi-perimeter minus the side. The only difference that you might want to note is here you're going to multiply an extra semi-perimeter, where in Brahmagupta's you don't. In our first example of this section, we want to find the area of the triangle. So we'll need to use Hero's formula, and Hero's formula uses the square root of s times the quantity s minus a times s minus b times s minus c. So we want to calculate what s is, and that is the sum of the sides divided by 2. So we'll get 50 divided by 2, which is 25. And then we'll go back and plug it back in. We'll take 25 times the quantity 25 minus 7, 25 minus 23, and finally 25 minus 20. So go ahead and do the calculations on those. You can use your calculator. And that gives you square root of 4,500, which if you reduce that, that's 900 times 5, which is 30 square root of 5, which is the area of that triangle. And our last example. Find the area to the nearest tenth. I should probably make a quick note about the previous formulas that we used. You'll notice, or probably notice, that right here it says cyclic quadrilateral. basically, that means it can be a quadrilateral, but it needs to be able to fit inside a circle. So you cannot just apply this formula to any quadrilateral. So now, looking at our new problem, this cannot be inscribed in a circle. Therefore, we have to look at it a different way. What you should notice, hopefully, is that it is created by two triangles, and we have all three sides of the triangle. So what we can do is we can take the area of this triangle first, and then double it to give you that, to get the full area. So, to find the semi-perimeter, we'll add the sides again, divide by 2, you get 11, and we'll go ahead and plug that in. 11 times, and I'll just do the subtraction, 6 times 4 times 1, you get 264, 16.248 approximately, and keeps going. We'll double that, and that approximately gives us 32.5 units.